All right, everybody there? It's good. Yeah. Sorry, I was dealing with an issue from another class, a previous class. I've got one that sort of backs onto this one.
Can I ask you a question about lab?
No, not really, Julie. Not right now. Can you ask me after the class?
I'll try to remember. Thank you.
Okay. If it's about the class, I'll take questions about the class. That's what you.
No, it was just about the due date of the spectroscopy lab. Are we supposed to be doing it in lab or not?
Yeah, that's right. But you can, if you want to do it beforehand, you can.
Because it's due right after. That's why I was asking.
That's right. Yeah, but you know the plan is we'll get it done during the lab. I'll be helping everybody with it. So it should be doable. Is that okay?
Yeah, it's great. Thanks.
I have a question before we move on with the new material. Can I ask it?
Yeah, if it's
so I know for the integration you mentioned that for peak 7 ppm the following applies, and then you said a 4H would be an aromatic ring with 4 hydrogen attached, and a 5H would be an aromatic ring with 5 hydrogen attached. I get the 5H because I can picture a C6H5. For the 4H, can you help me with the structure? I mean, I can only think of one 5 chain with an oxygen.
No. I'm just. Yeah. Can you see? You should be able to see my screen here.
Yes.
There's actually 3 possibilities, but I'm going to show you. This is what I'm talking about with 4H usually. So you got 2 things attached. I'm calling them X and Y.
I see. So we're still having a 6 carbon. We just have two
things coming off the chain.
Okay.
Two things coming off the ring.
Gotcha. Okay. Thank you.
Okay. Generally at each end. Doesn't have to be. I suppose there are 2 other possibilities where the X could be in different positions, but we're generally talking about this situation. Okay.
Okay. Thank you.
Anybody else have anything about the previous classes we've gone through? Any questions? Okay. All right, that's good. Let's see what we're doing here. Now, as far as infrared spectroscopy goes, I really want you to kind of be on your own with that. The problem you'll get on the test does not really need infrared spectroscopy to solve it, but I'd still like you to go through this information on your own. I have some videos as well that are in the mini lectures folder that relate to this. I'd like you to go over those yourselves. If you have questions about it, you can ask during class, and we'll probably go over something like this towards the end, like on the review day. So if anybody has any questions then, but you know, it's not really going to be entirely necessary for you to be able to do this to solve the problem. It'll be helpful, but you're kind of on your own going through the infrared stuff. I know that there's people who've never seen it before, but it's not really that bad. Okay, let me go down and show you where it is here. Let's see, here we go. Introduction to IR spectroscopy, infrared spectroscopy, peak shapes and locations, and then infrared spectroscopy examples. So those 3 are the videos that I'd like you to watch for that, please. Like I said, I'll give you a little bit more guidance on the review day when we're going over that kind of stuff. Okay. So we're going to start here on aromaticity, and we're looking specifically at aromatic systems. So let's start with that. So I'm going to give you a bit of a, well, it's going to be a fairly quick and dirty explanation here of what's going on. I can't access those links. I'm going to have to do a, I'm going to stop the share for a second on this. All right. I'm having some difficulty finding the thing here, but I need to be able to access here.
Yeah, those 3 links that are on that that page, only the middle one actually still works. So.
Right. Okay. Yeah, I'd have to download. I can't download the thing here on this computer, unfortunately.
You get to see your drawing skills?
Well, not really. I don't really want to do that. Dang it. It used to be much easier to find these things, but for some reason. All right, let me do a search here. Here we go. All right, this looks like it's going to be okay. All right, so to start out with here, we've got benzene. Benzene is a 6-membered ring. It's got 3 double bonds alternating. And what you'll often find is there's two ways it could be represented, 3, I suppose, if you count everything that's happening here. But we've got 3 double bonds, and they can be alternating. They can be in either place that you see here on the screen. But often what we'll see is it represented as a circle, because this situation is what we call a resonance situation, meaning that the double bonds actually aren't in these particular stable locations. It's actually alternating between the two so quickly that we can't even distinguish between them. So over here, this gives you an explanation or a little bit of an idea as to what makes benzene so special as far as its stability goes. So I've got this little graph here with the energy. And what this is showing is the reactions of these compounds with hydrogen gas. Now I know it looks a little complicated, but you'll see what I'm talking about in a second. So when you take cyclohexene, which is this compound, so only got 1 double bond in the ring, and you treat it with hydrogen gas, I might do a little bit of drawing over here to help with the explanation. don't know why this is not working out so well here. Here we go, it's better. Maybe it's not straight. Okay, so if we treat this with hydrogen, we'll end up with cyclohexane, and it'll also be plus 28.6 kilocalories per mole. So what that tells you is that gives you an idea of the energy tied up in that double bond. Now, if you've got two double bonds, we still end up with cyclohexane as a product here. Oh gosh, that's awful. And the energy there is 55.5 or 55.4 kilocalories per mole. Can anybody tell me what the relationship between those two is? Any thoughts?
Can you hear me?
Yeah, I can hear you.
So would that be because of the energy of the double bonds?
Yeah, well, but what's the relationship between the two numbers here? Just approximately.
They're twice each other?
Yeah, it's about twice each other. Two double bonds, right? I think it makes sense. If you've got two double bonds, you'd expect it to be twice the energy, right?
Right.
So that's what I'm getting at. Now, if you were to, and this is a theoretical compound here because it's not really the way that it is, but what we know is that double bonds are shorter than single bonds. So if this compound existed and the double bonds were not in resonance, can anybody, well, actually, you've got it here. It would be plus 85.4, which is about three times, or 85.8 kilocalories per mole. Now, this doesn't exist, by the way, but if it did, that's what we would get from it. That's what we'd expect. Now, as it turns out, if you look at benzene, real benzene, it's actually 49.8. It's actually lower energy than the one with two double bonds in it. So what I'm saying is benzene is actually about 35 kilocalories per mole less than the one with the theoretical three double bonds in it, but doesn't exist. And if we look at benzene, the other thing we know is that all of these bonds have the same length, which tells you that, and it's a length that's intermediate between the double bond and single bond length, which tells you that the electrons are all just in resonance all the way around that ring, that they're not stuck between two of the carbons as I've got here in this diagram. So there's a reason, there must be some sort of reason that this has a much greater stability than we'd expect it to have. And it's due to that resonance leading to a whole lot lower energy than we'd expect it to have if these double bonds were set within this ring as I've got here. Does anybody have any questions? So we're going to figure out now why that is, why benzene is so much more stable than we'd expect it to be. Now this is going to look a little bit complicated initially. I'm going to have to give you a little background as to what's going on in this diagram here. I know it looks very nasty. Now I'm going to take this back a little bit. I know that a lot of you, well, you should have done molecular orbitals, at least to a degree, back in Chem 2 or possibly Chem 1. And you would have heard of terms of p orbitals and s orbitals and all of that. So I'm going to draw on your knowledge of that a little bit, I hope. But when we're dealing with a double bond, there's actually two bonds we deal with. And you would have dealt with this back in Organic 1. I know you would have. Don't lie to me. Don't lie to me and say you've never seen this before in your lives. but you've got a pi bond and you've got a sigma bond. And this is between two carbon atoms if we were looking at, say, a CC double bond. I'm not even going to ask if you've seen this before or not, because I don't want to know the answer if you haven't. So we've got these two p orbitals here that make up one of the bonds of the CC double bond, and that's going to be the pi bond. Now the pi bond itself, if you remember, is above and below the plane of the sigma bond. So it's top and bottom here, and that's what we're looking at. Now I'm going to introduce some new information that well, it should be semi-new, but might not be. I'm hoping that you've seen this before, but you might not have. Now there's two ways that we can arrange p orbitals to get a pi bond. So this would be the two p orbitals from the carbon atoms before they join, and then this will be the pi bond that we get from that, and that's a bonding orbital there, a bonding molecular orbital. That's what the MO stands for, molecular orbital. The other possibility is that I'll try this again. I don't like that diagram. Never goes better. See, this one is in phase, so these phases match. And these are with the phase that doesn't match. And you can see that what we get from this is what I'm calling anti-bonding. So this is an anti-bonding molecular orbital. Now what we know about these is that the anti-bonding is a whole lot higher energy than the bonding. So this is a good situation, and this one is a bad situation down here. Does anybody have any questions so far?
Yeah, I do.
Yeah. Mm-hmm.
Is it still, when it's in the antibonding phase, is it still a bond?
Not really. No, it's actually the absence. It's the absence of a bond, but it's more extreme than that. It's a bad situation. It's the electrons are in the wrong place if it's happening like that. You'll get a better picture of that in a second, Julie, when you see what I put. I'll give you a little bit more context for that. Okay. So if we were to transfer this now to the situation where we've got not just a bond between two carbon atoms, but the 6 2p orbitals that go around the benzene ring, then I'm hoping that you can see that the lowest possible energy would be the one where everything was in phase. So that is, we have plus, 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 plus all the way up the top and minus, minus, minus all the way down the bottom. That's the best possible energy. The worst one would be alternating, and you can see that here, where we've got plus up the top, plus down plus down the bottom, plus up the top, plus down the bottom, plus up the top. So I'll stop there for a second. Does anybody have any questions about, this is just energy that you got here on, and the possible energetics of these situations. Is everybody okay with this being the best and the one that's alternating being the worst? Does anybody have any questions so far? The other situations that you're seeing here are different combinations, again, some worse than others. And the ones that have the greater amount of overlap between the good phases, those are going to be lower energy than the ones that have not as much overlap. So you can see here, these are the other 4 possibilities. And I'm not going to go through them, but these are the other 4 kinds of combinations. And it turns out that the 2 down here are of equal energy, and these 2 up here are of equal energy. But these tend to be anti-bonding because there's more anti-bonding going on than bonding. And these are bonding because there's more bonding going on than anti-bonding. So what that leads to is, let's see if we can, if it's got the diagram here. I was half expecting it to show the diagram, but it doesn't. All right. So the final diagram that we look at here for benzene looks like this. And we've got 6 2p electrons, which means we've got 6 electrons. And the 6 electrons go like this: 1, 2, 3, 4. Now, do you remember Hund's rule, which states that if you've got 2 energy levels that are the same, the 2 electrons go in one at a time, 5, and then 6. The 6 comes from the 3 double bonds. So when you've got the 3 double bonds here, 1, 2, 3, that's 2 electrons in each. That's a total of 6. And this is what the energy diagram looks like. Now, these places where these slots here match what we've got down here. This corresponds to the lowest energy. These 2 correspond to the 2 that you're seeing here. And these 2 correspond to these 2. And the top one corresponds to this one. You'll see that the electrons are never in anti-bonding orbitals, which makes it a much better situation. Does anybody have any questions so far? Julie, I still haven't answered your question, but I will get to it in a second once we look at a different kind of situation here. All right, let's look at this case here of a 4-membered ring, and I want you to compare the two things that we end up with.
Where are the 2 p orbitals for the other one?
These 2 here?
Yeah.
Well, it doesn't.
For the one on the bottom.
Either one of these, the situation's the same. It doesn't matter if these are up or down. It's still going to end up giving you the same kinds of energies. So if this had the plus on top and the minus on the bottom, or had the minus on top and the plus on the bottom, it still wouldn't change the situation here because you'd have just the same amount of overlap.
Mm.
Is that okay?
Yes.
Okay. So let's look at the case of the 4-membered ring. Now, one thing you'll notice is that in order to get these 6 energy levels, what I can do is I can take a benzene ring and put it on its end. And you can see, oh, that's terrible. And you can see that anywhere there's a carbon atom, we can put an energy level. So that's one way of being able to tell how many energy levels you expect to see. So if you've got a 4-membered ring, here's what I would want you to see. We could put it on its end. How many energy levels do we expect? We expect 4. And this is them here. So we can go through and we can show where we expect the energy levels to be. So for the lowest one, what can you tell? Can anybody tell me what the phases are going to be? What the phases are going to look like for the lowest energy one in the 4-membered ring?
All in the same direction, so
Yeah.
all positive on top, for instance.
Yes, all positive on top. That's good. I'm sure that's what somebody put in the chat. Now, what about the top one? The worst energy level. What's that going to look like?
Alternating.
That's alternating. It's good.
When you have rings like this, it usually messes me up. And if you draw a midline on benzene, for instance, you've got 3 that are above that line, and we know those are anti-bonding, and 3 that are below, and that's anti-bonding. But when you have something like this, where a midline is going to go right through 2 of them, does that mean that the only bonding one would be the lowest? Yeah, exactly. So how does that work?
I'd say that's technically anti-bonding. If it's
so both of those are anti-bonding as well as the top one. So
yeah,
really the only bond very
that's
bottom
right.
one.
That's right.
Okay.
I'd say that's true. Now the other 2 cases are the other 2 possible combinations. So we can do plus, plus, minus, minus, and then plus, plus, minus, minus. And then the other one here, see that's for this one. And the other one here has the same energy. And that would be plus, 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 minus, and then plus, minus, minus, minus. So both of these have the same energy on that for the other possible combination.
Both of which?
Sorry, this one that I'm putting the arrow to, and this one. They have the same energy. They have the same amount of overlap and lack of overlap.
It's hard for me to see. They both have 3 minuses and a plus, or 3
Yeah.
plus and a minus. Is that what you're saying?
Well, both have the same amount of overlap going on, or the lack of overlap. Because this one has overlap between 2. This one has overlap between 2. They're just adjacent, but lack of overlap between the other 2. And if I wanted to, I could have just simply not drawn this one in, just like they did over here. But the point is that 2 of the combinations are the same energy, and that's all I'm trying to get at here, Julie. So how many pi electrons are we dealing with in this case, if we've got 2 double bonds? Anybody want to guess?
4.
4, that's right. 1, 2, 3, and then 4. So this is what I was talking about earlier. This is a horrible situation now where we've got 2 electrons that are in separate orbitals, and they have to be placed there because those orbitals are the same energy. It doesn't have a choice. So if this existed, what it would look like is this. It's kind of crazy. This compound doesn't really exist, by the way, but if it did exist, here's what it would look like. It is just super crazy, but you've got the double bond here, which is the 2 electrons in the bonding part, And these two here, which are effectively antibonding, they can't bond. They have to remain as two separate electrons, just sitting there, longing to bond, but can't. It's kind of like a star-crossed lovers type situation. They long to be together, but can't be, because they're the same energy.
Why aren't they all overlapped? Like, why couldn't they all be overlapped?
Because it's just, well, in the case of the 6, it's not a problem, right? Because the three sets all end up in the clearly in the bonding section of the energy diagram. Whereas here, we've got two combinations that are actually effectively anti-bonding, because the two electrons are going to have to be placed into separate orbitals. And that's what I mean by those two arrows. They're both pointing up in separate orbitals. So it means that they're two electrons in separate orbitals that can't bond together. And that's a horrible situation.
I might be jumping ahead just a little bit, but on the videos, you were giving this as an example, and ultimately it comes out to be anti-aromatic. But you
Yes.
said, but in reality, this would technically twist, becoming non-aromatic.
It would, yes. You see, this doesn't exist in this way at all, because it's just
Okay.
it's just too ridiculously energetic. I mean, the thought of having two electrons here that can't bond together. So what they'll do is, you see, this only matters if this is flat. So what it will do is it will actually twist out of the plane. This is highly exaggerated, but it will twist out of the plane so that those two electrons can actually bond. So if it twists, then this is no longer a problem, because it's no longer flat. So if you were to beat this down with a hammer to make it flat, the two electrons would actually unbond. Do you understand that, Donna?
I do. So, but in terms of, here we are on your test, and you say, here's this, we're assuming that everything is planar. We're assuming that it is flat.
Exactly.
So based on the flat, that's the answer you want, not
yes.
in reality. Okay.
Yes.
No, I mean, it's helpful to know what reality does, certainly.
Yeah, that's right. So it turns out that there's certain numbers of predictable patterns. Some will be aromatic and some will be anti-aromatic. This particular case is anti-aromatic. So this is anti-aromatic. This is the worst possible situation. The benzene situation is the best possible situation.
So and we're talking about the left version is anti-aromatic, and the right twisted one would be non-aromatic, correct?
Yes, that's correct. That'd be non-aromatic. Why? Because it's no longer flat.
Okay, thanks.
So here's what we know, and this is called the Hugh-Cool rule. So if you have 4n plus 2 electrons, pi electrons, that's aromatic. And that would mean examples would be 6, 10, 14. These are magic numbers for aromaticity. 4n pi electrons would be anti-aromatic. And that would be 4, 8, 12, etc. Anybody have any questions?
For the first one, it could also be 2, correct? Because the integer could be 0?
Yes. Yeah, but that's not a particularly common situation, but I can give you an example of that. a 3-membered ring with a positive charge in it and a double bond, that would actually the plus up here, I suppose, would be an example of that. That's got 2 pi electrons and the plus up here. But that's the only one I can sort of come up with off the top of my head for that one.
Okay. Thanks.
Now, if we look at the 8-membered ring that has 8 pi electrons in it, looks like a stop sign, and we do the energy diagram for that, it looks like this. So I put it on one of its points, and then I put the 8 electrons in. It goes 1, 2, 3, 4, 5, 6, 7, 8. You see, we end up with that same situation where the 2 electrons they can't bond together. So if it was flat, it would look like this. Let me see if I can draw it a little bit better. So that's what it would look like. It would look like with these 2 electrons here, and they'd just be looking at each other, couldn't bond. So what it would do is, instead of doing that, it would take the shape of a lawn chair instead, so that it didn't have to be flat. And if it did that, then it's no longer subject to the same rules because it's no longer flat. So they can bond together at that point. They can be together as long as this thing isn't flat. But you can see again, that's an example with the 8. This would be an example with the 2. So I suppose I could say 2 here. All right, any questions? Okay. Well, that's all well and good, isn't it? But you really want to know how you're going to be tested on this, right? You want to know what it looks like on the test?
Well, both.
Or both. Okay. Yeah, so let's not be unfair here.
As long as I'm clear about the testing part, yeah.
Yes, that's right. Okay. All right, let's go back to aromaticity. So here we go. So to be aromatic, the following conditions must be met. The system must be cyclic, right? Round, that means. All double bonds and or charges must be conjugated. By conjugated, I mean alternating. Single, double, single, double, single, double, all the way around, right? The system must be flat or planar. That's what we've been talking about. It has to be flat. And for aromaticity, there must be 4n plus 2 pi electrons in the system. So numbers are 6, 10, 14, etc. To be anti-aromatic, it's exactly the same conditions, except that at the end there's 4, 8, or 12. And everything else in the world is considered to be what I call non-aromatic. So anything that's not flat is automatically considered to be non-aromatic. All right, does anybody have any questions? Okay. So here is an example. Actually, I think there's one other thing I wanted to go through here. Yeah. Here we go. I'm not going to play this video. I'm just going to skip forward to certain. All right. All right. Can you all see this on the screen? These
Yes.
examples, right? So we're assuming everything here to be flat, and I've got what amounts to I've got three possible ways that we could say they're going to be aromatic, they're going to be anti-aromatic, or they're going to be non-aromatic. So looking at the first one, this one is cyclic. We're assuming everything to be flat, by the way, and it's alternating. So that one has 6 pi electrons, so we make that one aromatic. This one we've already looked at. This is the 4 electrons. That's flat. That one, because it's got 4, is anti-aromatic. This one's got 8, so it's anti-aromatic as well. Now, what about this one here? Any thoughts about this one? Aromatic?
It's not. It's a non-aromatic. It's not conjugated.
Right, because it's missing. If there needs to be a double bond here, if it was going to be that. What about this one? Oops. Sorry. All right. What about this one here? The one with the.
Not cyclic.
It's not cyclic, so that one's not aromatic as well. Now, what about this one? Any thoughts about this one?
10 pi, so that would be aromatic.
Yeah, it's got 1, 2, 3, 4, 5, and they're all alternating. It's flat and it's cyclic. So yeah, that one's okay. What about this one here?
8 pi, so that would be anti-aromatic.
Yeah, it's anti-aromatic. Anybody have any questions so far? Okay, this one here, now this one's a bit of a funny case. It's got 2 electrons here as a lone pair on the nitrogen, which can actually interact with the pi system, and it is alternating. It goes double, single, electron, double, single. So that one is actually aromatic, and these 2 are actually part of the pi system. So that's actually got 6 pi electrons, as does the one next to it. 2 of these electrons are part of the pi system, these other 2 aren't. With the charges, the plus here is the absence of an electron. So this would be 2 and 4, and it is alternating. So that one is actually anti-aromatic. The one with the minus here has actually got 2 electrons here. So that one would actually be 6 pi electrons. I'm going to show you these in more detail. So that one is actually aromatic. So anti-aromatic and aromatic. This one here with the 2 minus on it, 2, 4, 6, and then 2 extra electrons. That's actually 10. That one would be aromatic. And this one here, since it's not alternating, is not aromatic. All right. Does anybody have any questions?
Can you repeat the one?
I'm sorry. Somebody had a question.
Can you repeat the one? And that's just the oxygen with the.
Oh, this one?
Yeah. What
Yeah,
that?
so you got 2, 4, and you got these 2 electrons here that are part of the pi system, Bailey. And then this one here, these 2 electrons here are not part of the pi system. They're just sort of sitting out there. These 2 are actually overlapping with the others here. So that is actually aromatic.
Thank you.
How about the last one?
Yeah.
Why the negative charge can't be part of the ring? That would make it 6.
But it's not alternating. It's not conjugated. See, it goes like this. It goes double, single, double, single. Then it goes negative, single, single. See how it goes single, single?
Oh.
That's the problem.
Okay.
So it's not conjugated.
Okay.
This one is, it goes double, single, charge, single. So that's okay. All right, any other questions?
Why is the plus not the one next to it?
This one?
Yeah,
This one's anti-aromatic
because
because it's got 4 electrons. 1, 2, 3, 4, and then there's no electrons up here. So it's anti-aromatic.
but on the other one next to it, it only has 5.
No, it has 6. Okay, let me explain that. I was going to go into this because we're actually doing these specific examples, but I may as well do it now. Okay, if you've got a carbon atom with 3 bonds on it, and it's got 1 electron, this charge is actually 0. If you take this electron away, it's a plus charge. If you add an electron, that's actually a negative charge. So you can see that plus has 0 electrons, whereas the negative actually has 2 electrons. And neutral, which is called a radical, would have 1 electron. Is that okay? Anybody have any questions? Anna, do you want to ask a question? I'm not sure. All right. Okay. So, Julie, does that answer your question?
Yeah, I guess.
About counting the electrons, I mean? That the plus would be 0 electrons and the minus would be 2 electrons on that carbon?
Of the amount of electrons C has? Is that what, why?
Yeah, that's right. The C with the positive or the negative charge on it is what I'm talking about.
Thank you.
Okay. All right. What are we doing? That's right. Let's go back to here. Okay. So here's the question that you're just. It's this similar to what you'll be asked on the test, except the one you'll be asked will actually have a 7-membered ring. It'll have a 7-membered ring, and this one has a 5-membered ring. But you'll see it's a very similar kind of situation. Okay. So you'll be asked to fill in the molecular orbitals for each structure. State for each compound if it's aromatic, anti-aromatic, or non-aromatic. And for any aromatic compound, draw what it would look like if its geometry was planar. Okay, so let's look at and I do give you the diagrams. You don't have to actually come up with them on your own, at least the initial diagrams. So in the case of the minus for the one we just talked about and the plus here, you can see the minus has 6 electrons, and when we put the electrons in, you can see it comes out to be aromatic by the 4n plus 2 rule because it uses 6 electrons. The one with the plus has 4 electrons, 1, 2, 3, 4. And those 2 electrons, again, are just looking at each other. And that's the one that's anti-aromatic. And if it was planar, then it would be shown as an aromatic, so it would be shown as a double bond, and one of the double bonds would have 2 electrons. And it wouldn't matter which double bond you used and split apart into 2 electrons. Does anybody have any questions?
Number of arrows again? Sorry.
I'm sorry, Courtney. Could you repeat that, please?
How do you get the number of arrows again? I'm like lost.
Okay. So the arrows, in the case of the in the case of this one here, we've got 2 electrons for each double bond, that's 4, and then 2 electrons because of a negative charge here.
Why wouldn't you take 2 away if there was a positive though? You know what I mean? Like reverse of the negative.
Well, because actually I don't understand that question. I'm sorry, Courtney.
Like you know how the minus acts as 2 more electrons. So
Yes.
But what about on the positive? Would that not be 2 plus 2 minus 2 because of the plus? You know what I'm saying?
Well, it's 2 plus 2 and then 0 plus 0. It's
Okay.
0 is the plus is the absence of an electron.
Okay, so just
Do you see what I'm saying?
yeah.
All right. Any other questions?
I guess I don't really understand why that C just has 4 lines and a dot there? I don't know. I just don't understand why.
That top dot is a plus sign.
I understand, but I don't understand why it is.
I'm trying to sort through your question, Julie. I'm trying to understand what you don't understand. I'm sorry.
Well, you drew a picture of a C and you said showed three bonded electrons and one other electron, and you said that was 0.
It's neutral, yeah.
Why is that?
Well, we'll take this down a bit here to sort of take it back to basics a little bit. If you've got carbon, would you agree it has 4 valence electrons?
Okay.
Are you down with that?
Yeah, it says that on the chart. I looked.
Okay. So if we want to bond that to 3 hydrogens, which each have 1 valence electron, would you agree with that?
Yes.
All right. Can you see that I haven't added electrons from anywhere or taken them away, and there's no way that this could have a charge on it now in this situation? Would you agree with that?
Yes, but I don't understand why that C is not bonded. It's bonded to another C, isn't it, in the ring?
No. Oh, okay. Well, I think I see what you're saying. Okay. Remember, this is a line structure, so really, there's an H connected up here too. That's not being drawn in. Does that make it clearer?
Oh, that makes it worse.
It makes it worse.
Because if there's an H, you just said that one didn't have an H.
Oh, now I'm lost. I'm sorry.
You just said in the picture that you drew, you had a C, and you had 3 H's.
Yes.
And they were bonded to the H's. It's bonded to the H's. And then there's 1 electron left that isn't bonded to an H.
Right.
What's it bonded to?
Nothing. It's called a radical. They're very unstable. We don't often see these.
Where is it in the picture?
It isn't. It isn't anywhere. I'm using this as a means to describe why a negative charge would be the presence of 2 electrons on that C, and the plus here is the absence of an electron on that C.
It's just to symbolize it. That's all.
Okay.
I don't know how else to explain it, Julie.
It's okay. I think I can learn it without understanding it, maybe.
Well, that's unfortunate.
I know. I just don't. It's not clicking in. I don't know why.
Yeah, I'm really sorry because I can't really understand what you don't understand, and I'm sorry about that. It's not gelling with me.
It's okay. I mean, I'll take your word for it that it's. I understand that there's 4. I don't understand why that C has 3 H's connected to it. The picture you drew only has 1 H in it.
Well, I mean, I was trying to make it simple, but there's actually 2 C's here connected.
Okay, that's better.
And then those are going to have. Do you see what I'm saying? I didn't want to go down that road and have all those other things connected there. You know, I was just trying to give you an example, just trying to explain why we add an electron to that becomes negative. We take that away, it becomes positive.
But then you put that H in, and it looks like then it's now bonded to another electron.
I'm really sorry, Julie. I don't know what to.
It's okay. I'll figure it out.
I don't know where to go from there, unfortunately.
It's okay. Thank you.
All right. So well, all the stuff we've been talking about aside, does anybody have any questions about how we count the electrons? So if you're counting them, it's 2 plus 2 and then 2 for the negative charge, 2 plus 2 and 0 for the positive charge. That's how I want you to count them.
Question about like, yeah. So you know how like the peak is like a single bond to a single bond? How does that
Yes.
mess with the conjugation?
I'm sorry, could you repeat that please, Courtney?
Like of the pentagon, there's a single and a single that come together and meet.
Yeah, it's
Right.
actually single charge single, so it is conjugated.
Okay, so both of them count as conjugated. If there's a plus or a minus, it doesn't matter.
Yeah, it doesn't matter. Yeah, it's going to be the same deal.
As long as two singles are broken up, like on the test that are 7, the heptagon.
Yes. It'll look like this, Courtney. I hate drawing 7-membered rings, but yeah.
Yeah, they're hard to draw.
Right. For me to put 3 double bonds in here. So I do that. How many electrons do you see now? How many pi electrons?
6. I couldn't get it to unmute.
Oh, sorry, 6, right?
Yeah. So that would count as, wait, 6 is aromatic.
Yeah, that'd actually be aromatic.
Yeah, because the singles are broken up by the plus charge.
That's right. Now put a minus here. How many electrons do we have now? 8. Yeah. That one's anti-aromatic.
Okay, as long as the charge breaks it up. That was my question.
Yeah. So you can see that in the one you're dealing with on the test, it's going to be the opposite. The one that has the negative charge will actually be anti-aromatic, and one with the positive charge will be aromatic because of the extra 2 electrons in each case. So you'll see that, but I'm not really going into that right now for the 7. And then for part D, there's two possible scenarios. Well, you'll get one of them. The first one is asking which compound is more acidic, and the other possibility is asking which one undergoes SN1 reactions faster, and that one has a bromine on it. So looking at the one that's more acidic, acidity is the ability to produce an H+. So when we look at both of these compounds and we investigate what happens when we lose a hydrogen, so it's the same deal on the other one as well. So when you lose an H+, whatever is left has a negative charge on it. So this one would have, if you look at the anions, you can see that one produces a more stable anion than the other one does, because this one will be aromatic and this one will be non-aromatic. Now I'm kind of taking you back here a bit, because back in Organic 1 you would have learned about why one compound might be more acidic than another, and it all has to do with the stability of the anion. So the logic is as follows, is that if something's producing more H+, it's because the anion that's formed with it is more stable. So in the case of these two compounds, A and B, what you can argue is that because this anion, the one on top, is more stable than the anion on the bottom, then the compound that has the 2 double bonds in it is going to be more acidic than the compound that doesn't have any double bonds in it. And the difference in stability is due to the fact that we have aromatic versus non-aromatic. So the hierarchy of stability here goes like this. Aromatic is the best, followed by non-aromatic, followed by anti-aromatic. That's the worst. Okay. Does anybody have any questions?
So
That's the answer. Go on. Sorry.
the more stable most of the time means that it's more acidic, right? Depending on
Well,
what
the more stable the anion is, the more acidic the compound it came from is.
Oh, okay, thank you.
So if this is A, I could call this A minus. I'd call this B minus. The other way I could say is this: if since A minus is more stable than B minus, and it's important to get that right there, since is more stable than B minus, then I can say A is more acidic than B. And remember that A minus and B minus are different from A and B.
That's the anion, right? The anion.
Anion is A minus.
Right. Okay.
And B minus. So these are anions here. Is that all right?
Yep.
Does anybody have any questions?
Should it say then, since A minus is more stable than B minus, then A is more acidic than B?
Yeah, sorry. I didn't mean to write the B minus there.
Okay.
Sorry about that.
I actually remember from Orgo 1, yes.
You're right. Yes, you're right. It should be A is more acidic than B. You're right. Thank you. Okay, the other possibility, which compound A or B undergoes SN1 reactions more easily and why? We have to take this back a little bit and give ourselves a bit more background as to what happens during SN1 reactions. You can see that when we're talking about acidity, we're dealing with anions. When we're dealing with, I won't do the whole thing here. When we're dealing with SN1 reactions, then what we're dealing with is cations. So if you remember what an SN1 reaction is, and I know you've all done them, so don't lie to me and tell me you haven't. No matter where you went or where you came from, you would have seen this before. This is a typical SN1 reaction, and this is the slow step right here, which is the release of the bromine to produce a cation. And that is going to be determining of the rate here. So which compound undergoes SN1 reactions more easily? Well, the one that produces the more stable cation now will be the one that is going to be the one that undergoes SN1 reactions fastest. So looking at the diagrams, you can see them on the screen. I won't redraw them here for this one. You can see that when we take away the bromines from each one, in this case, we'll end up with a plus here. And in this one, we'll end up with a plus here. Does anybody have any questions about where I'm getting these cations from? So what that leads to is an anti-aromatic compound in the case of the first one, A, which I could call A+. And then this one, B, would give B+, which is a more stable cation. And the reason for that has to do with the hierarchy that I've got down here. Aromatic is better than non-aromatic, is better than anti-aromatic. Does anybody have any questions? So for this one, if we were to have A and A+, I would say that A+, sorry, in this case, B+. B+ is more stable than A+. So B undergoes SN1 more easily than A.
Dr. Musgrave,
Yes, Sylvia.
during the test, is it okay if we label it and respond with what you're writing out,
Yes.
or do you want us to draw?
No, you can write it as A+, B+, or whatever, as long as you're clear about what's what.
Okay, thank you.
You will see this on other people's tests as well. They've done it the same way. All right, so what you've got to understand is that it's going to be the stability of the cation that's driving how quickly the SN1 reaction occurs. The more stable that cation is, the more easily the SN1 reaction happens. All right, does anybody have any questions?
I might have missed it, but so if A is anti-aromatic, then what is B?
Well, neither A nor B specifically are aromatic or anti-aromatic. It's the cations that we're talking about here, Deanna.
Right. So if A minus is anti-aromatic,
A plus here, yes.
yes. So
is
what's
anti-aromatic.
What's B?
It's non-aromatic.
Oh, because there's no. Okay, got it.
Yeah, it's non-aromatic. So you can see non-aromatic's more stable than anti-aromatic.
Okay, got it.
Is that fair enough?
Yep.
Okay. Anybody else have any questions? Okay, that's a good place to leave it for today. So I will, I guess I'll see you all on Wednesday, on Thursday.
Thank you, Dr. Musgrave.
All right. See you all. Yeah, see you all later. Thank you.
Thank you.
Thank you.
I have a question.
Yeah.
So I was doing, it's about lab. It's really short though. I was doing the kinetics, like doing the calculations for that.
Yeah, yeah. Mm-hmm.
If we don't show out all of our algebra, like I wasn't showing like divide this by this to get K. You know what I mean? Like I was just doing it in my head.
I guess I'd have to see it, Courtney.
Yeah, I can send you it. I basically like, if I set the rate equal to K and the two molarities, right? But I didn't show K equals the rate divided by the molarity to the, like I didn't.
Well, I'd have to look at it. As long as it's clear what you're doing, then I'm okay.
Okay, I'll send you a picture of that.
Okay, thanks.
Thank you so much.
All right, I'll see you later.
I also have a question about the pre-lab.
Yeah.
Do you want us to take a picture and just submit it before class for, I already started. So I was just wondering, should we do that like ASAP or turn it all in at the end of class? Which would you prefer?
It doesn't matter. I can do it. You can do it either way.
Okay.
but I am going to go through it in class. So if
Okay.
you're having trouble with it, then would be the time to hit me with questions.
Okay, thank you.
Okay. Anybody else have any questions? Mary, you good?
Yeah, there was one question for the lab, but I'm sure you're going to go through it. It's about the first NMR diagram.
Yeah, I don't
it
really want
just-
to. I don't really want to
yeah.
talk about it until the lab,
That's all right.
since I will go through it in the lab.
Yeah.
Okay.
All right. Thank you so much. Have a nice day.
Okay. You too. Bye. Olivia.